McLean's Physics 30, and we're discussing mechanical energy, and this will be the last video I'll do in this series, and it'll be on question number 6. Two pole vaulters jumping over a height or a pole of an unknown height, and each of them have different velocities, but they have the same mass. So first off, before I explore the question in detail, let's look at what pole vaulters do. So in general pole vaulting, what you're going to have is you've got some kind of, you got your ground, and they have two poles and another pole between them, and the pole vaulters jump up and over this pole. And so they don't land into the ground. They usually have some kind of a mat for them to land on. And for this question, we're just going to assume that the top of the mat is level with the ground from which they launched. So they would come, they jab the pole into the ground, they use it to vault themselves up and over the pole, and then they land on the mat. And what they're saying to us is we have two different pole vaulters who are trying this, and they're both clearing the pole, and we know all the information for one of them, but not the other. The initial situation, the key part of the problem is the initial situation we're going to say is when they clear the pole. We don't care about anything before this. We only care about once they've jumped over the pole and they're on the descent down onto the mat. And when they hit the mat, we're going to call that the final situation. So now let's go look at the question at hand and see what we can do here. So two pole vaulters just clear a bar of height h. So that's important. So we can take our height that they're clearing the pole here is whatever the height of the pole is. So we can just use h in this instance. The first pole vaulter lands with a speed of 8.90 meters a second, while the second lands with a speed of 9 meters a second. So there's going to be a small difference in their kinetic energies here. The first pole vaulter cleared the bar with a speed of 1 meter a second, and assuming equivalent masses, so both pole vaulters are the same mass, what was the velocity of the second pole vaulter? And the question's implying for when the second pole vaulter cleared the bar. So let's start with some knowns here. We know everything about the first pole vaulter. So let's see if we can figure out what's going on there. So h here is simply h. We don't know what it is in this question. And the mass of the pole vaulter, we don't know, but that's okay. We've seen this in a lot of questions. And the first pole vaulter is going to land, so his final velocity is going to be 8.90 meters a second, and the initial velocity which he took off with is 1.00 meters a second, and we want to know how does all this factor out. And of course, as always, g is 9.8 meters per second squared. So let's go see how we can use this to solve the problem. So mechanical energy in the initial state is going to be equal, oh, I'm all over the place right now. Mechanical energy of the final situation. And as we always know, that's potential energy of the initial plus kinetic energy in the initial equals potential energy of the final plus kinetic energy of the final. So potential energy in this case is going to be mass times gravity times height in the initial state plus 1/2 mv squared of the initial state. And that's all going to be equal to mgh of the final case plus 1/2 mv squared of the final situation. So now let's see if there's some things we can cancel out. In this question, we have a velocity in the initial and final situation, so we can't get rid of that. But we can get rid of the final because we know he's going to land on the bag, and that's at 0. So let's see what we can solve from there. So the masses we don't know, and the height here we don't know. So this is going to be a bit of an interesting question. So what we're going to go ahead and do is we're going to see if we can solve this particular question. So now, if you factor the masses out, you're going to have mass times g hi plus 1/2 v, not w, squared equals m times 1/2 v final squared. And as we've always done before, mass of this guy is the same because we're only talking about pole vaulter 1, and his mass won't change as he jumps over the pole vault, so we can cancel them out. This will give us 9.8 meters per second squared times the height of the pole vault in the initial situation plus 1/2 times his initial velocity, which we're told is 1.00 meters per second, and that's all squared, which will be equal to his final kinetic energy, which at the moment is 1/2 v final squared, and his v final is 8.90 meters per second squared. So here, let's see what we've got. So 1 meter per second squared is just going to be 1 times 1/2 is just going to be 0.5 meters squared per second squared. And this part just carries on as we haven't done anything on this side yet. And over here, 8.90 meters per second squared is 39.105, or sorry, 8.90 meters per second squared times 1/2 is 39.105. So this is 39 point. Oh, damn it, I messed all that up. Three, two, one. And 8.90 meters per second squared times 1/2 is 39.605 meters squared per second squared. Now if I minus the 0.5 from both sides, we'll be left with 9.8 meters per second squared equals 39.105 meters squared per second squared. Divide both sides by 9.8, and you'll find that your initial height is equal to 3.99 meters, which is 4 meters, but we'll use a couple digits here because we need in the next step. So here we had all the information about the first pole vaulter, and that's what we can use to find the initial unknown height of the bar. Now that we know it, we can go on and figure out what the initial velocity of the second pole vaulter would have to be. So let's go on and try to find that now. So dealing with this one, find the known. So in this case, we're dealing with the same idea. We're going to have mechanical energy initial is equal to mechanical energy final. And just as we found with the last guy, if you work it out, is going to be the potential energy in the initial case plus the kinetic energy in the initial case is going to be equal to the kinetic energy at the end of the run. We should label these so we know what we're talking about. So H, we discovered this in the previous question. That's 3.99 meters. G we know is always 9.8 meters per second squared. V initial is what we're attempting to find in this case, and V final is 9. Let me confirm that, yes, 9.00 meters per second. And the mass again is simply mass. So if you use the same trick and factor out the masses, you'll just have gravity times the height plus 1/2 v initial squared equals 1/2 v final squared. And then here, this is going to be 9.8 meters per second squared times 3.99 meters plus 1/2 v initial squared, which we're trying to find, is all equal to 1/2 times the final velocity So 9 squared is 81 times 1/2 is going to give us 40 point. It doesn't want to give me my decimal. 40.5, there we go, meters squared per second squared. And over here, 9.8 times 3.99 is going to give us back that 39.102 meters squared per second squared plus 1/2 v initial squared. So now subtract 39.102 from both sides and you're going to get 2.796 remaining. Oh no, sorry, I looked at the wrong line. Cancel that. Sorry, makes more sense. 1.398 meters squared per second squared